Thank you, Chair, for chairing the session. And I am Prashant from IIT Bombay. I will be talking about nature of correlations in the composite fermion Fermi surface. This is a recent work, mostly based on a recent work done in collaboration with all these people, Maitreya, Amog, Zenbi, and Professor Janendra Jain. These are from Penn State. Ajit, who is in the audience from IMSC, and Shao Chuan, who is a postdoc currently at Princeton. And if I have time, I will talk about another. I will tease basically another upcoming work with Srijit, who actually cannot come here because he is giving a talk right now in another room. A BTech student, Arnav Jain at IIT Bombay, and Prasanjit, who is my PhD student. Okay, so this talk is about one particular point in the phase diagram of quantum Hall effect, and this has been the quantum Hall effect has been talked quite a bit about by Professor Jain 2 days ago in the evening, as well as Ajit yesterday, and perhaps a few more talks. But let me still reiterate the few basics and tell you why we find this one particular point in the entire phase diagram to be so interesting. So this is two-dimensional electron gas in a very large quantizing magnetic field, and you just measure Hall resistance of it, and you see this nice pattern in the Hall resistance. You see plateaus at 1/3, 2/5, 3/7. Actually, even before that, you see plateaus at these labeled by 1, 2, 3, 4. The Hall resistance here is quantized in the units of h/e square, and you have these integers correspond to this nu prime. These integers here 1, 2, 3, 4, they correspond to this nu prime. And how do we understand these integer filling fractions? Well, if I put electrons in a large magnetic field, they form Landau levels labeled by this n, 0, 1, 2, 3, 4. They are equally spaced in energy. And when I fill an integer number of those Landau levels, I get these integer states. So 1, 2, 3, 4, that's how I get them. But but interestingly, okay, I also, the experimentalists also see plateaus at fractional values of this nu prime or nu. Let's not distinguish between the two for the moment. So 1/3, 2/5, 3/7, 4/9, that corresponds to the sequence p over 2p plus 1. So p is an integer. And you also see them at 2/3, 3/5, 4/7, and so on. That corresponds to the sequence p over 2p minus 1. These are fractional quantum Hall states. And as the few talks before me have emphasized, you are essentially partially filling the lowest Landau level in this case. There is no kinetic energy. Interaction is the only term in the Hamiltonian, so it's very, very strongly correlated. And you see, and then you see these fractional quantum Hall states. So I am interested in a very particular point here, precisely at half filling, when the filling fraction is you fill half of the Landau level. That corresponds to taking p to infinity in either of these sequences. So you can either come from this side, or through these filling fractions from this side. When you take p to infinity, you get half filling. And there you see something interesting. Instead of a plateau, you see that Hall conductivity is a straight line, Hall resistance is a straight line, and then you see some non-zero dissipation. So Rxx is not 0, so it's a metal at half filling. And in fact, so why is this metal interesting? So experimentally you observe a gapless metallic phase, and in fact, if you look at these resistance oscillations, Rxx oscillations near half filling, they look very similar to oscillations near zero magnetic field. So based on that, you can say that perhaps you are seeing a Fermi surface emerging at a very, very large magnetic field in a situation where there is no kinetic energy. And actually, this prediction has been tested, that you do see a Fermi surface through several other experiments, such as anti-dot superlattice, Weiss oscillations. All of them indicate that a Fermi surface emerges with a particular wave vector kf, which you can relate to the density and so on. So this is the surprising thing, because the kinetic energy is quenched, only interactions are present. So how does a Fermi surface arise at such a large magnetic field? Well, so this is where the composite fermion theory enters, and it explains this phenomenon. So I think let me just just as a recap, tell you what the composite fermion theory is essentially you take electrons and attach two flux quanta or make it capture two flux quanta from the system, from the externally applied magnetic field to create another fermion, and that is called a composite fermion. And what it does, it simplifies the fractional quantum Hall effect. So, for example, at 1/3 filling, you have 3 external flux quanta per electron. So 2 of them get captured by the electron. You turn that into a composite fermion, and then you have 1 leftover flux quantum and 1 composite fermion that is filling fraction 1. So 1/3 state of electrons in terms of composite fermions is simplified to just an integer state. And similar thing happens at 2/5. You have 5 flux quanta per 2 electrons. If you capture 4 of them, you get 1 flux quantum and 2 composite fermions that is filling fraction 2. And similarly, the entire Jan sequence at p over 2p plus 1 maps onto the integer quantum Hall state at p of composite fermion. Now, something very special happens at half filling. You have 2 flux quanta and 1 electron. If you capture the flux, the entire flux is gone. So these composite fermions are experiencing 0 magnetic field overall, and this is why you are seeing a Fermi surface. So at the leading order, very leading order level, this is the answer, that this is why you are seeing the Fermi surface, and this at least qualitatively can explain all these quantum oscillations experiments. Okay, so that's all good as a picture, but does this picture hold up actually in some numerics beyond the beyond experiments in numerics? Does this picture hold? Especially, do composite fermions appear as low energy excitations of the system or not? So this is a nice construction. At least for gap states, it works very, very, very well. Do these composite fermions also explain the gapless states? So in fact, this was shown through a numerical calculation by me and Haldane in 2022. We took the lowest Landau level and Coulomb Hamiltonian. We did DMRG on this cylinder. We in fact did the dynamics on the cylinder, and what we could extract from it is the excitation spectrum on the cylinder. So you can then hopefully you can see a very faint straight line here, and you also see very strong some gapless spectrum here. But believe me, there is a straight line here, which yeah. So let's just yeah. Okay. So this straight line, in fact, the properties of this spectrum can be explained using a theory of composite fermions. So what you have to do is essentially you take the cylinder, it has a finite circumference in the y direction. What happens because of that finite circumference, the Fermi surface splits, the ky of the Fermi surface of Fermi sea of composite fermions gets quantized. So in fact, you see these 2 wires, the Fermi sea splits into just 2 wires, and using these 2 wires and then some prescription from composite fermion theory on how different operators look like, you can actually understand this spectrum quantitatively. So in fact, this work showed that composite fermions can indeed emerge at low energies as good description of the system. Okay, so that only answers an existential question, but there are much bigger questions which are there in this field. So it concerns the effects of interactions on top of your free Fermi surface. So you have got a model, and then you ask what happens when I add interactions. Now we know the answer for the regular Fermi gas. So if I add electron-electron repulsions on top of a free Fermi gas, I get a Fermi liquid. And Fermi liquid essentially behaves like more or less like a free Fermi gas. It has long-lived quasi-particles. You put an electron very, very close to the Fermi surface, it will live for a very, very long time. It will not decay into particle hole excitation. So it has quasi-particles. And then you just get a few parameters, few unknown parameters that you can fit from the experiment or numerics, etc. So in the presence of repulsive electron-electron or density-density interactions, a free Fermi gas we know doesn't do too much. However, as I will explain in a bit, the composite fermions interact via a different kind of interaction, and that interaction has been proposed in the past to lead to non-Fermi liquid behavior. So some things don't quite look like the Fermi liquid. So this is the major unsolved question in this field: is composite fermion Fermi surface, is it also a Fermi liquid in the presence of interactions, or does it become a non-Fermi liquid? Okay. Okay, so what is this interaction that is so special? Let's come back to the electron picture. So I have electrons, these red dots are electrons, and they are in this large perpendicular magnetic field, 2 flux quanta per electron. And remember that each electron I convert to composite fermion, and 2 flux quanta going inside this board, and this external field is coming out of the board. So overall the flux quanta going inside the board, they cancel the flux coming out of the board. Overall the magnetic field is 0. But now suppose these composite fermions move. Now if they move through this roughly analogous to Biot-Savart law, you are going to give rise to magnetic field coming from the composite fermions. And this will ultimately lead to some fluctuating effective magnetic field, and that gives rise to current interactions between these particles. And this is the current interaction, which is also long ranged in nature, which has been proposed to give rise to non-Fermi liquid, where the quasi-particle picture will break down. So if you put a composite fermion near the Fermi surface, it is going to decay very quickly. It is into collective excitations. It is not going to remain as a good quasi-particle. So now, based on this idea, we can make some predictions that can be tested later on. So what we are going to do, we are going to use this idea to make a precise prediction and then test that using microscopic models. So how do I do that? Well, I will use the field theory for this purpose. So let me start with electrons in a large magnetic field. So that's this Lagrangian. And then there are two versions through which I can convert this electron Lagrangian into a composite fermion Lagrangian. So one is called the HLR theory, where you introduce an emergent gauge field that couples to these little psi. So this little psi, let us distinguish that from capital psi. So little psi corresponds to composite fermion operators, and this little psi interacts with this little a. Little a is an emergent gauge field, and that in turn interacts with the externally applied gauge field capital A. So for example, so this capital A, for example, the density of electrons will be determined by little a and not composite fermions directly. There is another version of this theory where you think of these composite fermions as Dirac particles, as Dirac fermions. There are some differences between these theories, but for us it will not be important. But let me just explain to you what these different things are. So little psi is essentially an electron plus 2 flux quanta, and little a is the net magnetic field coming from the external plus these 2 fluxes going inside the board. So it's the net magnetic field which will fluctuate when composite fermions will move. So it is this which mediates the current interaction, this little a. Okay, so whichever theory I pick, it doesn't really matter for my talk. What you need to do is add Coulomb interactions to it. So Coulomb interactions for electrons. So you add a term, and then you use essentially a few definitions that you take Coulomb gauge. So little a is transverse A times something like curl of transverse A, but you divide by Q. Another thing is that you represent electron density as the emergent magnetic field divided by 4 pi. So with these two definitions, what you can do, you can essentially ask what is the effect of composite fermions on the emergent gauge field, and then what is the effect of emergent gauge field on the externally applied fields. So this way you can compute observables. So in this arrow, what I have done, I have gotten rid of the composite fermions, and I have written an effective Lagrangian which purely contains the dynamics of the emergent gauge field from the composite fermions. So this blue term comes from integrating over the composite fermions from this Lagrangian. So this is called the Landau damping term, and this red term is essentially just Coulomb interaction. And this is the transverse gauge field. In the Coulomb gauge, you represent it like this, and then the transverse gauge field couples to the temporal externally applied gauge field through this term. So what you see here is that the emergent gauge field is acquiring dynamics from the composite fermions, but these dynamics are damped dynamics. So what will happen is that the emergent gauge field will actually, whatever fluctuation of emergent gauge field you have, it will decay into the composite fermion excitations. It will lose energy by decaying into those. And then it is precisely this dynamics or this form, this Landau damping, which then is proposed to feed back onto the composite fermions and give rise to non-Fermi liquid. But let me say that this statement is uncertain. Theoretically, it is not on a very good solid ground. But this Landau damping is more or less robust. You just have to do RPA, essentially you integrate out fermions and you get here. Okay. Now based on this you can make a theoretical prediction, and the theoretical prediction is if I look at the equal time correlation function of the electron density, so this is electron density, that can be determined from this equation. So you are doing equal time, you are doing equal time correlation function. So essentially have to do an integral over omega of the propagator of the emergent gauge field, and ultimately what you get is that the static structure factor, the equal time correlator, is q cube times log of 1 over q. So if I divide S of q by q cube, it will diverge logarithmically in q. So this is ultimately what you get, and the prefactor depends on the kind of interaction you put in. So if you have Coulomb corresponds to eta equal to 1. So this will become 1 over 2 pi. So essentially this is the main equation that we are going to test. This comes from Landau damping, and you make a very specific prediction for the form of the static structure factor. So now you can ask, is this prediction going to hold when I do a more microscopic calculation? This is an effective field theory approach. We can now ask, is this going to hold in a microscopic computation? So for the microscopic computation part, what we do is we take the Jan wave function for the composite fermion Fermi C. So it is of this form. You take the Jastrow factor, which builds in correlations, and you multiply by the a non-interacting Slater determinant form for the composite fermion wave function. These are all many-body wave functions. This is the electron wave function. This is the composite fermion non-interacting composite wave function, and this is what builds interactions into it, and ultimately you project things to the lowest Landau level. So this is the so for us this phi CF is simply a determinant of plane waves. So recently there was a technological breakthrough in doing computations with these wave functions by two of my collaborators in a separate paper. So they developed a quaternion based technique to project these to the lowest Landau level. The advantage of that is that you can achieve extremely big system sizes. So you can go to something like 1,000 electrons, and then which is, it's very hard to imagine doing 1,000 electrons in ED, exact diagonalization, but here you can do that. This is quite phenomenal to me. So now let us just, I will not go into the details, but let me just go to the results directly. So what I'm going to do, I'm going to plot S of q divided by q cube. And the theoretical prediction is that it should be logarithmically divergent as log of 1 over q times some prefactor. So on the y-axis I have S of q by q cube, on the x-axis q, and this is the data. These dots are the data for different system sizes. So 400 electrons, 625 electrons, and 900 electrons. And you see there is barely any finite size effect. So there is no, I don't think there is anything is going to change beyond once we go to even bigger system sizes. And the dashed line, the purple line for example, corresponds to putting eta equal to 1 in this expression, and that has a logarithmic divergence. And the yellow line actually corresponds to putting eta equal to 0. So you see that the theoretical prediction that comes from Landau damping is in complete disagreement with the microscopic calculations from the wave function. This is a very strong result. This is done at half filling, as I mentioned earlier, and actually it doesn't really matter whether you do it for whether electrons are fermions or electrons are bosons. So you could do filling fraction 1 of bosons, and you see exactly the same result. Again, the data does not match at all with the theoretical prediction. And so at this stage, some people could question that, well, we do not know the Hamiltonian for the Jan wave function, so we do not know whether this state is a ground state of a good Hamiltonian or not. So recently I tried for just one system size. So I want to show you this data, but let me say that this is still up to, there could be, maybe don't trust this 100%, maybe trust this 40%, 50%. So what I did DMRG on a very big cylinder. So the circumference here is 26 magnetic lengths, where the Fermi surface has 8 wires. So these are 8 wires. And again, I plot the same thing, S of q by q cube versus qx. This is the data, these two lines. And again, the dashed curve is completely disagreeing. It's completely disagreeing with the theoretical prediction. And in fact, it is also saturating to a constant value, just like the Jan wave function. So how do we explain? So what we are seeing in numerics is that S of q is going like q cube. It's not going like q cube log q. So the log term is absent. And in fact, what we found is that you can explain the coefficient of the q cube term in a very precise manner. So this saturation value at roughly 0.21, actually this is 2 over 3 pi. I will show you why it is 2 over 3 pi in a bit. What you can do a mean field theory version or non-interacting version of composite fermions forming a Fermi surface. But now imagine that they are dipoles. So they have dipole moment perpendicular to their momentum. This particular form has been argued several times in many papers. So using this, let me just say, using this idea, you can again make a prediction for the static structure factor that comes out to be 2 times 2 nu cube by 3 pi kf cube. So if I plug in nu equal to a half, you will see 2 over 3 pi. If kf is 1, you will see 2 over 3 pi. And this 2 over 3 pi explains the DMRG data perfectly, and also it explains this data. So the black line that you almost cannot see is actually the theoretical prediction from this dipole theory. So the theoretical prediction is matching extremely well with the numerics. And similarly, at nu equal to 1, you also see this black line perfectly matching with the data. How much time do I have? 10 minutes? Okay. Okay, thanks. Okay, so this simpler model where you have composite fermions as non-interacting good quasi-particles, etc., and they are dipoles, that model explains both the Jan wave function answer and also the DMRG ground state result in the q tending to 0 limit. Let's see. Okay, so what do we do with this disagreement between microscopic computations and the field theory? Now, it turns out that the Landau damping is a robust prediction. As far as I know, it is also independent of Landau parameters. So you cannot argue that you have some Fermi liquid parameters which change the coefficient. So as far as I know, it is quite robust. Now, there are multiple possibilities here with the field theory and this disagreement. Well, one thing is you just accept that Landau damping is completely absent. There is something wrong with the field theory, and you need to fix the field theory. There are some more subtle possibilities. For example, the coupling between external fields, capital A, and the emergent degrees of freedom, like the composite fermion and the emergent gauge field. Those couplings might be modified, which is why you are not seeing Landau damping in the electron density correlation function. So it might still be there, but it's just that your electron density operator is not sensitive to the Landau damping. That is another possibility. So I was thinking about this, and then there is indeed some subtle things that happen with this dipole term, but Hoffman in 2021 has shown that in fact that does not matter. So what really happens is that when you add this dipole term to the field theory, you get two contributions to the electron density. One comes from the emergent magnetic field, the other one comes from the dipole of composite fermions. Now what happens is that because the density of composite fermions is proportional to the externally applied magnetic field, some cancellation happens between this term and the gauge field dependent part of this dipole term. So ultimately the electron density operator becomes completely independent of emergent gauge field. But even with that, Hoffman has shown in 2021 that Landau damping is not modified. You are still supposed to get q cube log q naught over q. So that cannot be the explanation that the coupling is, I think it is less likely that the coupling is getting modified. Okay, so let me summarize here. So as I have shown you that numerics on Jan wave function, they indicate absence of the contribution from Landau damping, and this is also supported by DMRG. And the numerics match really well with a non-interacting dipolar picture of CFs. And from here we can ask a few questions. Now you could have noticed, suppose we accept the microscopic answer, the numerical answers, you may have noticed that both DMRG and the wave functions are actually matching really well with the dipolar CFs. But you might think that once you include Fermi liquid parameters, the coefficient of q cube might change. So that could be one direction where one could ask whether Fermi liquid parameters modify the dipolar CF. Another big question here is, what should I really observe? What should I measure in DMRG or in the microscopic wave functions to observe non-Fermi liquid behavior if there is any. So we are now working on some of these questions, but I think I'm out of. Yeah, is this complete? Okay. I'm wondering if I should go to the second part of the talk or finish. How much time do I have? Okay, so let's
25
go.
is over.
25 is over, so then let's finish. Okay, so let's finish here. So I will not go into the second part. Yeah.
Thank you. So the talk is open for questions.
Thanks, Prashant. Very nice talk. So in these DMRG simulations, where you get basically the Fermi surface breaks up into these streams, can you somehow estimate if you go the quasi-particles away from neutrality, you get some sort of a Fermi surface within your volume is finite.
Okay.
In the DMRG, of course, you don't have a Fermi surface. You have Fermi points because you
Right.
open up your. Are there some tricks that you can do in your DMRG to extract how the Luttinger volume scales as you dope this point? Go away from it.
So the way we know to dope this point is by changing the number of electrons, by changing the filling fraction of electrons. Now what that does, it introduces an effective, non-zero effective magnetic field for composite fermions. So you don't get a Fermi surface now, you get Landau levels of composite fermions. So then the question of Luttinger volume, etc., become more subtle. In fact, there are some unsolved, or there are some issues with the Luttinger volume slightly away from half filling. But
in an experiment where there is disorder, interactions, and everything,
yes.
when they dope it, they would see. They don't know about this. The wave functions that are being used. They will see a Fermi surface, right?
They see some oscillations which then they interpret from the Fermi surface picture, and they try to find KF, etc. Yes.
And you can make contact to what KF they would observe.
Yes. So KF is. It is related to, so the Luttinger volume is satisfied here. So Luttinger's theorem is already satisfied. So what you can do is, I mean, in one dimension, Luttinger volume relates to the length of the wires. You can just sum up the lengths of the wires. It matches with the density of, so the Luttinger volume matches with the density of electrons at half filling.
And I think that was the question. So you map it to a 1D problem.
Yes.
The original problem, your infinite 2D plane has a particular area.
Yes. So you can rewrite a new Luttinger's theorem, but for the wires, and that is satisfied.
But that will not be the Luttinger area that the experimentalists are going to see, right?
So experimentalists don't directly see the Luttinger area, right? They see some cyclotron orbits, etc. So from that they extract KF. So I don't know precisely how to connect, but we know at half filling the Luttinger's theorem is indeed intact. But away from half filling, then it is more subtle. Yes. Maybe I can discuss that later on, but yeah. Yeah.
So Prashant, why do you, so this Landau damping you are saying is robust, but I thought it's some large and not controlled and things like that, right?
Yes, but so it has been shown that if you do more diagrams, so this was a paper by Yongbek Kim et al. In 90s, that now suppose so first you do RPA to find the propagator of the gauge field, you feed it back to the fermions, then you again feed it back to the gauge field. It turns out that the RPA answer survives that. So at least at that level we know, but okay, beyond that, if you want to sum up infinite number of diagrams, I don't know the answer.
Yeah, no questions for that. So thank you.